Hi everyone, welcome back to IGNOU's classroom. Today we are going to learn about discrete probability distributions. So the last video we were talking about what are the basic concepts of probability. We saw what an experiment is, what a sample space is, what an event is, the different types of probability distributions that we assign, right? The standard one, the relative and the subjective and all. So today we are going to further discuss about probability distributions and mainly focusing on the discrete probability distributions part. Okay, so uh, in the first module we talked about the distributions, right? Frequency distributions. Like for example, if there are 10 students in a classroom, and after giving a unit test, if we were to find out a frequency distribution of all the marks that the 10 students in the class got, how we do it, all those things were discussed in the very first block of MMPC file, right? Now we are talking about probability distribution. So what is probability distribution? In frequency distribution, if you remember, we were talking about the counts of occurrences, right? Suppose say there were 10 students and the marks they obtained out of 10 were say 5, 6 and 7, 7 being the highest and 5 being the lowest. We would count how many students got mark 5, how many students got 6 marks, and how many students got 7 marks, and we used to write the counts against each of those values, and that's how we found out the frequency distribution. Now in the same way, for the number of what you can say, if we plot the values, that is the possible outcomes in your sample space and their corresponding probability of occurrence, then we will get a probability distribution. Now, so in short, what we can say is a probability distribution is the representation of all possible outcomes and their probabilities. Like for example, if you toss 3 coins, say the experiment is tossing 3 coins. So, and we are interested in finding how many heads come up, right? So, in say one toss of coin, we know it is half and half, right? Now, if there are 2 possible tosses of coin, maybe there will be no heads, maybe there could be 1 head, or maybe there could be 2 heads, right? So this is the possibility, right? If in the first toss it is either no head or it is 1 head, if you are tossing 1 coin. If you are tossing 2 coins, you can get maximum 0, 1 and 2. And similarly, if you are tossing 3 coins, then you may end up with such a probability, such possible outcomes, right? And now, what is the probability that each of this occurs? Like there are no heads at all, or there are all 3 heads falling, just 1 head is falling, or just 2 head is falling. What is the probability of all these things? If we plot it, we will get the probability distribution. Now, so what you can say is that, like there are possible outcomes will be definitely 0, 1, 2 and 3, and against each of this we have a probability value assigned, right? Now this probability value, we don't know what it is, we need to find out, but we know that it will definitely be between 0 and 1, and it will, and each of these possible outcomes can be assigned such a probability, right? So this you can say is like a function of, if you call this h, and this is a function of h, right? So if this is the variable, then this is a function of that variable, correct? So from this what we can say actually is, so this is like an uncertain real variable, right? And this is an uncertain real variable over here, and it can assume multiple values depending upon the outcome, right? Multiple values depending upon the outcome. So this is the outcome. And so this thing what we are talking about over here, this uncertain real variable called h, this one, for to which we can assign probabilities, is what is called as a random variable. Okay, so this is the random variable, because at the time of tossing the coin we don't know, we know for sure that it could either be one of these 4 outcomes, but we don't know for sure which of it is going to be. And for each of these outcomes, we know that there is a particular probability that can be assigned to it. We can calculate and assign a probability. So this is called a random variable. That is this one, the outcome is represented using a random variable. So these two concepts of what probability distribution is and what a random variable is needs to be understood, so that we can when we go ahead we can build on this. Okay, now in our case of tossing 3 coins, we know that it is either going to be a 0, 1, 2 or 3. That is, there is a discrete set of outcomes, right? Independent and discrete set of outcomes. So when we are dealing with such random variables, the probability distribution is called a discrete probability distribution. But take another case. Maybe we are trying to predict the weather, or maybe we are trying to predict the amount of rainfall, or even the exact weight of, say, a 1 kilogram of rice packet. Okay, so even if you say that you're buying 1 kg of rice, sometimes it may be 0.99996 kg, or sometimes it may be 1.002 kg, or it could be anywhere between this, right? We can't exactly measure 1 kg. So what happens is that our random variable is not discrete. It is not exact value. It is very difficult to actually pinpoint all the decimal possibilities, right? So in those cases, our random variable is assumed to encompass a continuous sequence of values. Like in our frequency distribution in block 1, we had continuous class intervals, right? Similar to that concept, our random variables over here will fall in a class. Okay, so such probability distributions are called continuous probability distributions, and the method of analyzing them and finding inferences from them vary slightly, just like how the methods of finding mean, median or mode for a discrete and continuous classes were different. Similarly, we have slight differences here also. So in today we will talk about the discrete probability distributions, where our random variables will be discrete values. So finding the probability mass function or the probability distribution function. So generally when we talk about discrete probability distributions, we talk about the probability mass function, and for continuous distributions it is the probability distribution function. Okay, now simply when we take the probability distribution, what we know is what we can expect from what we can see is what we know from the past outcomes. Like previously when we tossed a coin, this is what happened, or previously when a bag of rice, 1 kg bag of rice was packed, this is what happened. Now with probability mass function or probability density function, PDF is probability density function. I think I wrongly said about it a little while back, right? My mistake, sorry. So PDF is probability distribution, probability density function, and PMF is probability mass function. Okay, so with this PMF or PDF, what we can infer is what we can expect from the future. The next time I toss a coin, what can I expect? That is what we can find from these. Okay, so we can assess the PMF or PDF of a particular random variable in different methods. Like for example, we can use a standard function, or we can use the past data. When we use past data, we should make sure that the conditions similar to what was there in the past would prevail now also. And we can use subjective assessment. So these 3 methods come directly linked to the kind of probability we are assigning, right? We had standard probability assignment, where if there are n outcomes, we are considering the probability for all those n outcomes to be equal, that is 1 by n. And when we are using past data, means we are assuming the probability to be a relative probability, and subjective assessment is when we assume the probability to be a subjective one. Okay, now how do we use the standard functions? Sometimes what happens is that like we said, we need to identify the underlying process in that particular experiment. Like if we are tossing a fair coin, then we can say that the underlying distribution is going to be a standard one. If we are tossing an unfair coin, then it is going to be a relative probability, right? So we need to first identify the kind of process here, okay, that best explains our experiment. Like for example, you can say that if suppose our experiment followed the Bernoulli's process, then we should be using a binomial or Pascal distribution function. And if it is a Poisson's process, then we should be using a Poisson's distribution to find out the PMF or the PDF. Now, when can we say that the experiment is following Bernoulli's process? How do we identify that? Now, for that we have three questions that we can answer. Okay, the first is we need to find out whether the events that are coming out from the experiment, the outcomes of that experiment is it mutually exclusive and collectively exhaustive? Mutually exclusive means, suppose you are tossing a coin. So if you're just tossing one coin, then that particular coin will either fall on its head or its tail, right? If the coin falls on its head, then naturally it has not fallen on its tail, right? You might find it funny, but this is the thing. So that is what we mean is over here, that if something happened, then the probability of the others happening is not there. Like both of them can't happen at the same time. It is mutually exclusive. Like I hope you get that point. Okay, so that is very important and should be collectively exhaustive outcomes in the experiment. That is, there should be a fixed set of experiment. It's either going to be a head or it's going to be a tail. It should be collectively exhaustive. Okay, and repeated observations of the experiment, the probability of occurrence of these events should remain a constant. That is, no matter how many times you toss the coin, it will either be a head or a tail, right? That 1 by 2 probability will definitely be there. And the observations are independent of one another. It is not like you tossed one coin, it fell on the head, and then if you toss one more coin, then the probability of a head or tail is not at all dependent upon your first coin toss, right? No matter what happened in your last coin toss, if you toss a coin right now, it's either going to be a head or a tail. It's not going to be dependent on your any of the previous or the upcoming experiments, right? So in such cases, if if your experiment satisfies these conditions, then your experiment is following a Bernoulli's process. Okay, so that is the easiest example is definitely the coin tossing or the success failure situations, like either the student failed or the student passed, or either a machine produced a defective item or a correct item, non-defective item. Okay, such experiments or such situations are Bernoulli's process. Now, if the process is a Bernoulli's process, the experiment is a Bernoulli's process, then the random variable of that experiment, which we will be interested to know, is either the number of success or failures in a specified number of trials given the probability of a success in a trial. Okay, that is, if there are 12 tosses of a coin, maybe what is the number of heads that I can expect, or what is the probability of heads I can expect, something like that. Or if the number of trials needed to have a specified number of successes, like for example, if I want to get 75% success rate, then how many trials I'll need to conduct. Okay, then such PMF or PDF, such distributions that we need to find out means, then we need to be using the binomial or the Pascal distribution. Now, what is the binomial distribution? Now, to find the PMF, that is probability mass function of a binomial distribution, then that is the number of success or failures in a specified number of trials given the knowledge on probability of a success in a trial that follows a Bernoulli's process, is the the function, okay, is NCR P raised to R Q raised to N minus R. This is NCR means the the combination. Okay, the now combination, all the possible combinations of N trials and R successes, and P raised to R is the probability of success in a trial, and Q raised to N minus R, or Q is over here the probability of failure in any trial. That is 1 minus P actually. Okay, so first how NCR, that is the number of combinations of successes, okay, in N trials, probability of success in a trial, and multiplied by the probability of failure in any trial. If we do that, suppose say for the first trial, then if there are totally say 10 trials, then for the first trial it will be like this. that is 9. So 10C1 probability of 1 and into 9. So this will give the probability of the associated with that random variable for the, let's say, for the first for the first trial, like that. Now suppose it is a Pascal distribution, then Pascal distribution usually comes when we need to find the number of successes. um, then what we do is, first we need to find out the probability of r minus 1 successes out of n minus 1 trials multiplied by probability of success in the nth trial. That is, suppose say we are doing let's say an experiment where mm, suppose say it is a medical trial. Then if we have already done 100 trials, what is the success, what is the probability that the medicine will work or will also be a success in the 101th trial? Or we have already done 99 trials, we know the probability of successes in these 99 trials, then what is the probability of success in the 100th trial? Such cases we use this. Okay, so and this is the formula. So first we will find out the probability of r minus 1 successes in n minus 1 trials. So this is kind of like an extension. Okay, it is an extension of the um, previous distribution we saw over here, the binomial distribution we saw over here. So r minus 1 successes out of n minus 1 trials means n minus 1 combination c r minus 1 probability of r minus 1 into q raised to n minus r multiplied by the probability of a success in the nth trial. Now, so that is, if the experiment is following a Bernoulli's process, we can find the probability distributions in these two ways. Now, what if the experiment is following a Poisson's process? So Poisson's processes have events that are occurring randomly over a time period. Okay, and such cases, what we use is, we use the Poisson distribution, where we try to what you can say, we try to find the long run average, and based on that we find out the Poisson distribution. Okay, so lambda over here represents the long run average. So the long run average, we are exponentiating it with x, where x is your random variable. Okay, and we have an exponential factor over here, which we are again raising, we are finding it to the power of the long run average, and the whole divided by x factorial. So this PMF is usually used to represent distributions of several random variables. Like for example, maybe spare parts, or the number of telephone calls per hour, or defects per meter of a bale of cloth, such things. That is very long running processes. If we want to find out the probability of maybe a defective piece coming out, or there is some issue over there, or in mass produced cars, maybe there is one car where there are certain problems to the engine or something like that. Or maybe if it is a cell phone, what is the probability that one of those cell phones out of that mass produced batch becomes may have some problem with the display, or may have some heating issues, whatever it is. So such cases we go for this Poisson's distribution. And Poisson process so corresponds to a Bernoulli's process, but with a very large number of trials and very low probability of success in any trial. So in this case, when we talk about success, what we mean is, say, a demand for a spare part, or there is a heating issue. So that is what we are talking about success. That is, so it is usually in the mass production sector that we apply Poisson's process. So from this, what we can say is that the PMF or the PDF, it gives the whole probability distribution for a random variable. Okay, so so that is like very vast. So very vast number of trials, that, and with each trial we can, with this simple formula, if we already know this formula, all we need to know, all we need to do is substitute. We need to know for one experiment what is the probability that each of those come, what is the probability of success, or what is the probability of failure. We just need to know that. Like if it is a coin tossing experiment, for one toss of a coin, what is the probability that a head would fall or a tail would fall? That is 1 by 2 and 1 by 2. We already know what is the success probability P and failure probability Q. Now, no matter how many number of times you toss a coin, we don't need to, so based on the number of times the coin gets tossed, like if it is 3, then the number of heads could be ranging from 0 to 3. If that is 12, then the random variable would range from 0 to 12. That's it. So no matter how much it is, since we already know the probability, it will be NCR P raised to R Q raised to N minus R. All we need to do is N will be the number of your trial and R would be the what is the random variable value. So if it is 0 means 0, 1, 2, 3 like that. So N will, if you are talking about 12 tosses of a coin, then N would be 12, and in that R would be either 0, 1, 2, 3 like that up to 12. So for each of it, all we need to do is we just substitute the values and we find out the probability, nothing more to it, right? It makes our work very easy. Okay, so sometimes, but we are interested in finding the probability of a group of outcomes. Okay, so such cases, what we do is, we talk about the cumulative distribution function or CDF. So that why? Because we will be in such cases we'll be interested in finding the probability of that random variable would take with values less than or equal to a particular quantity. Okay, and what? So suppose say there are maybe 12 tosses of the coin. We just need to find out, say, the group of probabilities between 5 and 6. Okay, there are either 5 heads coming up or maybe 6 heads coming up. So what is that? In that case, this is where we talk about the cumulative distribution function, and what we do is we generally add up the probabilities up to that given quantity and it will give us the cumulative distribution function. Okay, now, so now we have our distribution function, that is probability distribution function. Now we need to infer, right? We are doing all this to get insights from the data, to get business insights and make decisions, right? So for that, it is not just enough that we get the distribution function. Now we need to summarize it and apply it, right? So we have few summary measures and their applications here also, just like how we had it in our frequency distributions in block 1. So the first is the expected value. Expected value is the return you can expect for some kind of action. And what you can say, it is the mostly used, we can think of as investors when they use this expected value to estimate the worthiness of the investment. If I invest in so and so company, what is the expectation of return? Like what kind of a return can I expect from this particular investment in, say, within 1 or 2 years, or maybe within 20-25 years? What is my expected return? That is what we can find out from this probability distribution of a year. So it is what you can say, calculated based on the relative riskiness. Okay, so the modern portfolio theory and a lot of theories use this expected value to reach at those conclusions. So we will maybe know more about it when we take the finance papers, financial investment papers. We will be using these things. Now, how do we find this expected value? It is calculated by multiplying each of the possible outcomes with the likelihood that each outcome will occur, and we sum it, like the probability of occurrence of a particular outcome multiplied by that outcome. Okay, and we sum everything up and we find out the expected value. The next is the standard deviation, that is the degree of dispersion or scatter. Same to how we used to find the standard deviation in our frequency distribution. It is kind of like the same formula only, where this mu is nothing but the expected value here. Okay, so x of I minus your minus your mean whole square multiplied by the probability of occurrence of each. So in our first block, this probability of x of I was nothing but our frequency, right? And then whole square. So this will give the standard deviation, and you square it, you get a variance, almost the same, right? So this is how we are using discrete probability distributions, and in the next class we'll talk about the continuous probability distributions. And if you like this video, or if you found that this is useful, if it is helping you and you've come this way, do consider subscribing. It will help me make better videos. It will be an encouragement for me also. All right, so thank you so much. See you in the next video. Bye.